We're going to work on example number 1, in which we're looking at a bus moving over a certain distance, okay, and it's got certain velocities at certain times. So that's the objective here. Now, I'm going to be using sigma notation, which is going to be new for a lot of you. And I'll try to explain it in each problem as I go through. As we get further along, I'll explain it less and less because I'm assuming you're getting more comfortable with it. If you're not comfortable with the sigma notation, you need to go out and watch some outside videos, or you need to email me, or whatever happens to be, to get used to it. So the idea for determining the total distance that something has traveled, so we'll look at the change in the distance that something's traveled. That's equal to the velocity over some time period times the change in time. Okay, so for example, let me give you a very basic example. Let's say that you're traveling at 30 miles per hour and you travel, okay, at 30 miles per hour for 2 hours. Well, then your change in your distance is equal to your velocity times your change in your time during that period. So the change in your distance is equal to your velocity, 30 miles per 1 hour, times the amount of time that you traveled that velocity. So 2 hours. So your hours cancel out here, and you're left with 30 times 2, which is 60 over 1, and miles is your only unit left. So we traveled 60 miles, and that makes sense. Look, if you go for 2 hours at 30 miles per hour, then of course you're traveling 60 miles. Now let's say, for example, that during the next 3 hours, you travel at, I don't know, 45 miles per hour. Okay? Well, now your change in distance is equal to your velocity 1 times the change in time 1 plus now this new velocity times its change in time. So your total change in distance will be equal to the first guy, which we had, plus, now you increase speed to 45 miles an hour, so 45 miles per 1 hour, and we're going to do that for another 3 hours. So your change in your distance is going to be equal to the 30 times 2, the hours cancel out, and so again we're left with the 60 miles there, plus here the hours cancel out, and 45 times 3 I believe is 135. Just doing that in my head real quick. So this tells us that our total distance that we've traveled, the change in our distance of our vehicle, is 60 plus 135, or 195 miles. It's that easy, okay? Let me erase this now. Now let's talk about the sigma notation. The sigma notation says this. For this formula, our change in our distance is equal to the sum, which means add all the velocities at some I times the change in their time at some I, from I goes from 1 to n, where n is the number of times that we're changing speed. Okay, this I is a lower bound. Okay, well, the I itself is the index, the variable that we're using. Okay, I equals 1. 1 is the lower bound. N is the upper bound. Okay, and so what this right here stands for is it says, okay, take 1 and plug it in where you see I in your formula. So I'll plug in 1 where I see I. And I'll add to it, I go up one value from 1. So I go to 2, and I use the natural numbers. So I go from 1 to 2 to 3 to 4. So now I go from 1 to 2. So my next one is v2 delta t2 plus. Then I go to 3. So it would be v3 delta t3 plus. And that goes all the way up until I hit n. So the guy right before n is vn minus 1 delta t n minus 1. And the last guy then is a velocity at n times the amount of time that you traveled. Whoops, that's got to be an n down here. Okay, the change in time of the not the unit, but of the interval, or whatever you want to call it, of n. Okay, so this shorthand right here is equal to this massive mess down here, and that's why we write it like this. It's a condensed version. So getting to the problem, it says that that the bus. So we're looking at a bus, okay, and the bus travels 4 meters per second for the first 2.5 seconds, and then it travels 5 meters per second for 3 seconds, and then it travels 3.2 meters per second for the third 2 seconds, and then it travels 1.4 meters per second, okay, for the fourth 1 second, so for just 1. Okay. So let's go ahead and do the computation here, and then we're also going to take a look at a graph of this. Okay. So let's go ahead and draw the curve for velocity. I want to show you what's going on here. So for the first 2.5 seconds, we're at 4. So let's say this is our velocity. I'll get to this. I'm going to get to this formula in a second here, but I want to do this first here. And then let's say this is time. Okay. So it says for the first 2.5 seconds, we travel at 4 meters per second. So here's 4, here's 5, here's 3.2, and here's 1.4. Okay. Yeah, just make it nice and easy for us. So for the first 2.5 seconds, okay, we're traveling at 4 meters. It's at a constant velocity. Okay. Then we jump from for the next 3 seconds, so from 2.5 to 5.5. I want to get some room down here. Okay, so this first length, this is change in t1. Okay, the change in time 1, and that's equal to 2.5. This guy right here, I'm not going to do this because I don't want it to get confusing. So change in t1 is, I'll just write it below, okay? So change in t2 would be equal to 3. And now from 2.5 to 5.5 seconds, we're traveling at 5 meters. Okay, let's do my best to get my line. 5 meters per second, okay? Now, so clearly this function is not continuous. Now, for the next 2 seconds after that, so to 7.5 seconds, this length is a change in time 3, and that's equal to 2 seconds. And during that time, we're traveling at 3.2. Okay. And then over here, 1 more second later, so 8.5. This length in between here is going to be the change in time 4. Okay. So that is it's just 1. Okay, just 1 second. Okay. Now, that guy's got a height value, so we'll go ahead and put that guy's height value in there, just like that. Okay. Now, what we're doing is we're taking this and really dividing it up into little rectangles. And why are we doing that? Well, look, when we look for the change in the distance, that's, for us, it's sigma I goes from 1 to 4, our n value is 4, of each of the velocities of I times their change in time sub I. So what this guy expands out to is we take 1 and we plug it in there. So we have V1 delta T1. Now plus, and the reason we do plus is because we're summing, plus V2 times delta T2 plus, now we go to 3. So V3 delta T3, and then we go to 4. So that's V4 delta T4, like that. Okay. Now we just got to plug these guys in. What are each of these guys? Well, the first one, V1, is the velocity over interval 1. Okay, so that's 4 meters per second. And then we multiply that by the change in the time over that first change in the time period. So that's 2.5 seconds. And now the seconds will cancel out, and I'll be left with just meters. Now I'm going to stop writing seconds here. I'm going to stop writing meters, okay, just to save myself some space. But we know that the end result is in meters. So this is V4, the velocity, times the amount of time that we were at that speed. Now what is this really? Well, that's 4, so the height of 4 times the length of 2.5. So what we're calculating there is really the area under the velocity curve. So this is the area under the first section. That's area number 1. Okay, now that's really important because later we're going to have velocity curves and we're going to ask how far a particle traveled. And to figure out how far a particle traveled, how far its distance changed, we need to know the area underneath the velocity curve. Okay, now velocity 2 is 5, and its change in time is 3 seconds. So that computation right there is this area right here. So this is area number 2. And now, this guy right here, velocity 3 is 3.2. Its change in time is 2 seconds. Okay. And this guy right here is area number 3. And of course we got one more. So velocity 4 is 1.4. The change in the time is just 1. And that whole guy right there is area number 4 on the graph. So what we're going to do now is just compute those guys. So let me go ahead and grab a calculator here. So 4 times 2.5 is 10. 5 times 3 is 15. 3.2 times 2 is 6.4 plus 1.4. So if I go ahead and I add those together, I believe I get 32.8. Now of course we were in, our dimension is in meters. Okay. So big picture, and this is important, the area under a velocity curve tells us how far an object traveled during that time. Okay, so what we're saying is from 0 to 8.5 seconds, over that amount of time, our object traveled 32.8 meters. So 32.8 meters in 8.5 seconds. And if you understand this story here, okay, you're in really good shape because a lot of your physics will be based off of off of this idea right here. Okay, in fact, I can remember this semester helping some students on their physics and discussing how far a particle has traveled, and we had to use the area underneath its velocity curve.